Hey everybody, I'm using my teacher device or personal laptop sort of thing today, so I can use an applet that won't work on the school computer. So I could leave the camera on for a bit to say, hey, anyways, I'm trying to, I should look at the camera instead of myself, I guess. Anyways, let me turn the camera off and share my screen and we'll get going. Go, hide that. And here we go. So we're looking at significant digits, accuracy and precision, and error analysis. Okay, so this is the stuff that I've been talking about like um, how many numbers to keep when you're rounding and so on. We're going to get more official here, and well, yeah, I'll show you how it works. So as usual, there's a question sheet at the beginning. So first, let's start with just accuracy versus precision. So accuracy is how close the measurements are to what they should be, the true value of what they should be. Has more to do with the equipment itself, calibrated properly and so on, than to do with like carelessness or sloppy measurement. Whereas precision is how close the measurements are to each other if you do a bunch. So how consistent they are basically, and that often has to do with carelessness or faulty equipment or bad conditions or whatever. Okay. So for example, a digital scale can be very accurate, but if it's used carelessly, it could be imprecise or inconsistent results. Um, it can be inaccurate, but used very carefully, leading to very consistent but wrong results. We have a scale here at the school that just reads the wrong numbers. Doesn't matter how careful you are with it. So the difference between accuracy and precision is just one that often gets confused. They kind of seem similar, but yeah. So if we were looking at a dartboard, you would consider this one to be accurate because it's in the bullseye area and fairly precise, but it's not all in the yellow, right? So this one in comparison, though, very accurate and very precise. Okay, this could have been like more spread here, and I would have been like, okay, not precise. I would say I'd be pretty happy with that result if I was using a bow and arrow, to be honest. Anyways, this next step here, this one here, super precise, super consistent, but obviously the sights are out, so you're skilled at using the bow and arrow, but it's the sights are out or whatever. And then this one, of course, is neither, right? It's all over the map, plus it's off center, so it's not accurate or precise. Just to help visualize the distinction between those things. Um, Preciseness, the repeatability is the idea of the consistency. Yeah, so just basically a little bit more of the same there. Okay. So controlling and reducing error in measurements. Your goal is to have as little error as possible, obviously, in measurements, especially in comparison to the size of what you're measuring. So, the level of precision is the device is kind of out of your control often, of course, right? But you can make choices in your experiment that makes the things you're measuring be as long as possible, which reduces your percent error, which we will look at very shortly. Okay, so like the period of a pendulum, for example, if we're measuring how long it takes for a cycle, instead of measuring the time for one cycle, you can measure the time for a whole bunch of cycles. In which case, you have a give or take a half a second error, maybe of your thumb hitting the stopwatch button. But a half a second in comparison to 1 second is a lot bigger error in comparison to the size of what you're measuring. It's literally half of the value, whereas that give or take half a second in comparison to 38 is a very small percentage of what you're looking at. Okay, so that's the idea of this. So, for example, if we were measuring the speed of a wave, you might be better to measure the time it takes for it to go there and back, because that's twice as much time, right? Or even more, there and back again, based on the reflections, right? Just get that time interval you're measuring to be as long as possible, so that your error is smaller in comparison to what you're measuring. Okay, it has less effect. With standing waves, if you were measuring a wavelength, instead of measuring one loop and doubling it, which would double your error to double the size what it normally be, instead you could measure 3 loops and calculate what the wavelength would be. Right, 3/2 wavelengths would equal the value, and you'd solve for wavelength. Multiply by 2, divide by 3, and so on. I can't really draw can't really draw too well on the screen here because it's my device. But so if we had the 3/2 wavelength equals, say it was 5 meters or something, then you would multiply both sides by 2. So multiply by 2, get rid of that, right? Show the times by 2 there, whatever, in scribbles. And then we could divide both sides by 3, and so on. You can picture how you would get the values here. Did an extra dash there by accident. Yeah, you get the idea, right? Oh, that's good. Get rid of that piece. Touch screen on my new device is so much worse than the original device, last devices we had. Anyway, so that would be 10 divided by 3. You'd get a number for the result, right? And again, your error is smaller than in that case, it's a smaller percentage, of course, right? So this percent error that I'm talking about, there's two types. There's percent deviation and percent difference. Sometimes people use different words, but basically the concept is the same. If you're comparing two experimental values that are sort of on equal footing, if you don't have a reason to trust one more than the other, then you want to just find the difference between the values. And those bars at the end, you might have seen those in math class. That's called absolute value. Okay? Absolute value just means you don't care if it's a negative. You just do the positive version of it. There's no such thing as a negative percent difference. You just talk about the percent difference. I guess there is negative if you're above or below the expected value, but we're just interested in how far off, right? Doesn't matter whether it was above or below. And you're going to compare those measurements to the average of them, because one doesn't have more, more weight or reason to trust versus the other one. You just want to know how different they are from the average of them, and that's and then you just multiply by 100, stick a percent sign on it, of course, right? So that's how you do percent difference if you're comparing two experimental values, two things that you've measured by experiment. Oh yeah, different high school labs. If you're doing high school labs, it's typically 10% or less is considered pretty good. I have to figure out how that might work for us. So for example, here, just to show why this is true, why there's less percent error, considered way less error. If you measure in an experiment a value of 10 and a value of 12, right? It's only off by 2. What if you measured this number here, 2 million, versus 2 million and 2? They're still only 2 off. So is that the same amount of error? Well, no, of course not, right? Because a difference of 2 in comparison to 11 is, so there's my negative value. I happen to put them in that order, and so it becomes a positive, and you're just like saying, okay, well, it's, you got 0.188%. So it's 18.8% percent difference. Okay. If we're looking at the millions version, we're dividing in comparison to, or dividing by 201 million. And so it gives us a much, much smaller percentage. It's like 0.0000999%, right? This experiment 2 has almost no error whatsoever in actuality. And then the relative error, the percent error, is almost nothing in comparison to what you're measuring, in comparison to the first one where it was almost 20%, right? So yeah, the bigger the values you're measuring, the less your percent difference can easily be. Okay, so make choices to make that happen, right? Worst case scenario, if someone's measuring a length in a room, they measure the length of one tile and then multiply it by 30 to get the length. That's terrible because you have the error in that one tile multiplied by 30. Versus instead, you might measure, if you only have a certain length measuring device, maybe you'll measure 10 tiles and then divide to get what one tile would be more accurately, and then multiply that by 30. Picture the difference, right? So there's choices you can make as a scientist that lead to better results. Okay. The other type is sometimes called percent deviation. The main idea, though, is you're comparing an experimental value to an accepted value, a known value, like what it should be, right? So that kind of counts for more. What it should be counts for more. And so what you do for that one is you do your accepted value, take away your experimental value, or the other way around. Doesn't matter because we're going to absolute value it. But you compare it to, you divide it by the accepted value and then slap the 100% on it, okay? So for example, if you're measuring the acceleration due to gravity, it's supposed to be 9.8. By experiment, you found it was 11. Well, then you'd have 9.8 take away an 11, absolute value of that thing, and you end up with your percentage ends up 12.24%. So we'd hope for a little better results than that if we were doing a high school lab. Okay? So that's the idea of percent error, whether you're comparing to known values or just comparing two experimental values that are on equal footing, sort of speak. Okay. So transitioning into that actually is the first part, and that's actually this part, error analysis. It's a different order here. I guess I should rearrange that, but it doesn't really matter, of course, right? And accuracy and precision all sort of taken care of. That's going to come up in the next part we do, and what next part we do leads to significant digits. So let's get started on that. I have screenshots from the applet that I'm using, but I'm just going to use the actual program right here. Okay. So this is a little activity, digital virtual activity that used to be in the old online course. It probably isn't anymore because I had to go through a couple hoops to make this program run because they killed Flash a little while ago, right? So um, Flash isn't used anymore. So it says, let's do some math. Let's put two 2-meter rulers together and see how long it is. And basically, like, okay, well, it's around 4 meters. Of course, it's logical, right? So let's measure our length with. We're going to compare in the pages later about to the official, perfectly, thought of as perfect length of an actual meter. Um, and so basically, there's a 5-meter version apparently to make a precise measurement. We talked about precision being like the how many decimal places. This little blurb here talks about the same precision and accuracy stuff we just talked about, right? So accuracy would be more about repeatability and how careful you were, whereas precision is sorry, other way around. Accuracy is the one that's about how close it is to the right answer. Precision is about how careful you were. Sorry about that. Anyways, you can pause and read that, of course. So what do we have here? So it says, it's about 4 meters, and be like, oh, wait, or is it? And then they zoom in, right? So if we zoom in on it, you'll see that it's, a little less. Like, in other words, the exact version of a 4 meters might be a little different than any given piece of wood in a physics classroom, a meter stick and so on. So, that it's not exactly right, of course, but it's close enough for regular everyday purposes, basically, is the idea. Right? If you have, the more divisions, if you look at a meter stick, there's a side often with no millimeters and then a side with millimeters. So we'll talk about that soon as well, but hopefully you've seen a meter stick before, and if you can grab one in a class somewhere, if you're in real classes or in-person classes, whatever you want to call them, look for a meter stick and go ask a teacher if you can see one or whatever. Quite often one side has just centimeters, no divisions of millimeters, and the other side has millimeters. And we'll look at that soon here as well. So it says, what's going on here. Of course, if you're measuring something that's 32 meters long, you want to have a fair as close as possible results and so on. Should we consider that 4 meters there measured by the meter sticks not accurate? And they say no. Like, they say no, it's not that it's not accurate. It's just it's not like super accurate. It's good enough for daily basis, basically, right? So accuracy um, would be how close it is to the accepted value. And so, I would argue, based on what they've shown, that it's not quite accurate, of course, right? But they say, in short, no, of course, because it's close enough, right? So, you're not really adding any value to maybe everyday measurements about whether a car fits into a container, they're saying, if you're using a meter stick like that, because it's close enough. And sometimes it's not a great idea to have a bunch of extra of numbers, like decimal places that you can see, right? To have those extra decimal places, that extra precision in the number. They're using the word precision a little fast and loose there in comparison to how we just talked about it, right? But the more precise you're measuring something, more carefully you're measuring something, the more decimal places you can sort of include. So there's a connection there that we're going to go with. Okay, so basically, it wouldn't be beneficial to have your speedometer say 102.37591. It would just be confusing to have all those extra numbers, right? So it wouldn't be adding value; it would be worse. So it says, why is the International Bureau of Weights and Measures near Paris? So the wood meter stick isn't perfect, of course, and the answer for why it's in Paris is because they did the measurements originally to calibrate things and so on. There's a kilogram that's if we had an iron block that was 1 kilogram, clearly that's not going to stay exactly 1 kilogram over time as it rusts and pieces fall off. And so they have this platinum and iridium, 1 kilogram chunk that's under 2 layers of glass and blah blah blah. It's protected and so on. So they did this. They decided at one point that they don't want, after the revolution, they didn't want the based on the king's foot for a length and so on. So they started to define the system international units, or the international system of units, SI units that we call it, right? So the meter in French is to measure, and so that's how the name got coined from that point on, right? So the international units for length, mass, and time are, of course, meters, kilograms, and seconds. And that was established in France uh, just after the revolution. Any history buffs could maybe tell me what date that would be. Um, so mass is no longer measured in pounds and stones and so on. It was the kilogram, and they introduced the metric system with powers of 10 and so on as well. I'm just gonna go pause for a second here. All right. Hopefully, the group of students that are in the hall at lunch here weren't loud enough for you to actually hear, but they're kind of driving me crazy. So I closed the door. Here we go. So mass of 1 gram is defined as pure water at its maximum density. So that based on the temperature. That's at 4 degrees Celsius. If you're interested, look into weird properties of water to do with ice and so on. Has so it's not practical to do that on a daily basis. So instead, they made one out of platinum uridium, and it's kept at Sèvres, whatever that is, right? Wherever that is in France. Okay, it's probably a museum or a science center or science establishment or whatever. But and then they went beyond that. They actually sent some people, 2 French scientists, to measure the distance from the equator to the North Pole. And it took them like 5 years, it says, to do this. And then they took that and they divided it into a whole bunch of pieces. They sort of decided in advance for some reason that they're going to, divide it into pieces. So 10 to the -7. So take that distance, divide it by 10, 7 times, and be like, that's the meter. Um, I don't know why they went to that length, but anyways, that's apparently where the original length of a meter was established. So they returned with a meter stick, and they made a platinum uridium standard of it, and so on. I think it says later in this little activity, but the meter is actually defined very, very specifically now based on a certain number of wavelengths of light at a very specific frequency, right? So it's not based on temperature. The problem with even a platinum uridium stick is it's going to increase and decrease in size based on temperature and so on, whereas light travels without a medium, right? You don't have to have air for light to travel through, so it's a very more concrete and stable definition of the length. Time, of course, already they tried to do a metric version of time, but of course everybody was sort of so used to 24 hours a day and 60 minutes and 60 seconds and all that stuff. So I guess the proposal was like 10-hour days with 100 minutes in each hour. And, it kind of seems to probably 100 seconds in each minute and so on, but it just never caught on because people are so used to the regular length of an hour. To reduce it down only 10 hours would be kind of weird. Hours would be really long. That never caught on. So what do we have here? The atomic standards. Yeah. So it's basically even I think maybe it talks about the length. Yeah. So the length, they don't really say it, but it's actually based on frequency, number of wavelengths of light. Like I said, the kilogram is still dependent on the little chunk of uridium platinum, unfortunately, and so they're trying to kind of find a better way, right? So you made silicon sphere or a watt balance, whatever that is, and or reestablishing in terms of a certain number of moles of carbon-12, since we're a carbon-based life form. Like, it's basically they think maybe one of those might sort of win the battle and become a the new standard for the measurement of a kilogram. But it says until then, until a comet flattens Paris, each country must travel to France to make a near perfect copy of the real kilogram, so that they'd have, when you're measuring your scales in your country, a kilogram's being measured properly. So, yeah. What do we have here? The international system. So that's the idea of the meters, kilograms, seconds that I've already talked about. And so there we go. So it says basically here, how do those units compare to other stuff like volume and speed and so on? And of course, we know the answer. It's just based on those, like meters per second for speed, or meters cubed for volume from math class earlier in your career or your student life and so on. So they since though have extended the main three, the big three, to be the Magnificent Seven. So it includes the concept of a mole, the number of atoms in it, and the uh, the temperature scale for Kelvin, and the um, current measurement in amps, and light intensity in candelas, or lumens is often used as well. So with those seven measurements or seven concepts, you can explain everything. You can talk about the units of measurement for everything based on those seven. In our class, based on the three, everything works. If you even go to a grade 12 class and talk about the momentum of something, it's really just based on kilograms, meters, and seconds. All right, so how measurement is made and so on. This is getting into the idea of the significant digits. Okay, so the basically those numbers of decimals you would keep from a measurement. And so if you're using a meter stick like this that literally just didn't have, or not a meter stick, I guess it's 10 centimeters. So 10 centimeters, but there's no divisions at all. How accurate could you approximate the length of that broken piece of a candy cane? I would think maybe like, I don't know, around 4 centimeters or so, you might say, right? Because you just don't have a lot to go by. And then you look here and be like, okay, so now I can go a little more carefully here. So maybe it's like 4.3 or something. Because you have like, you can approximate, a fraction of this big division here. And then if you go down to this scale, then you'd be like, oh, okay, now I can go even more. And maybe it's like 4.25, like the more divisions you have on your measuring device, the more decimals you can state in your answer, or we consider that to be a more precise measurement. Okay, so you're being careful, so it's going to be consistent, so it's connected, but precision in the context here is really just about how to what level, or of in tiny increments, you are being careful to look at. Right, so those are our numbers that kind of make sense from what we get. It says increasingly more precise, but none of them are very far off from each other, right? So the accuracy was kind of like, we're all in the right ballpark. Um, so yeah, like you can't measure the fourth or fifth decimal place. You'd need some kind of special micrometer or something, a mysterious laser device, whatever that is, right? A lot of people quote that as like, oh, to increase my accuracy and precision in this lab, I would use a laser measuring device. And I'm like, can you look up one of those on Amazon for me? I'm curious what that would be. That, not sure it exists, but maybe it does. They wrote it here. But a micrometer certainly is more common. I have one in the garage for measuring parts on the Jeep. You're trying to identify what U joint you need. You got to measure the diameter of the caps and so on. Scientists distinguish the degree of precision by the number of significant digits. Okay, so this is very clearly just going to be one significant digit, two significant digits, and three significant digits, because there's literally just 1, 2, and 3. But there's more detail than that we're going to go through in the lesson, okay, about how to decide how many there are. So this looks like about 17.5 millimeters, right? Milliliters, sorry. And so you're like, okay, that makes sense. The uncertainty, how much error there would be, you might be like, give or take, 0.05 maybe, right? So the uncertainty would be like if you're approximating how unsure you would be of that. It could have been 17.4, it could have been 17.6, so maybe like 0.0, 0.1, I guess. 0.1 would be the sort of the error, the amount of uncertainty there is. So this is that silicon thing they're trying to make, and they want us to measure it. Okay, so we'll just do this because some of the numbers in the end are good. So we look at that and we say, okay, what would we just say this thing is like 3.6 maybe? So 3.6, and it's going to say, let's see if it likes my number there. So it's happy with my number. So it's based on the scale we have there. I actually, when I first did this, I'll show you. When I went in there, I was trying to like read the scale super fine. And if I was using a millimeter scale, I would say like 3.6 something, right? You can approximate that other decimal place. So maybe it's 3.65 or 3.64 or something, but they don't like that. They'd be like, oh, you have to only go to one decimal place, which I actually disagree with. Okay? If you have a millimeter scale, you can approximate a fraction of a millimeter. Okay, but to go with the program here, they show when you calculate the volume of that sphere, that you get this number. Okay. Does it make any sense whatsoever to include all of those decimals when you know this thing to be approximately 3.6, maybe 3.6 something? And then the read, obviously you have the formula for the sphere volume, 4/3 pi r cubed. And so you're ending up with like a ton of decimals because of, the way the calculations worked out of the 4/3 and the pi and so on. So the idea is, of course, you wouldn't want to trust the 5 and the 0, those very end numbers, right? Those clearly don't mean a whole lot. Okay. So since we started with, 2 significant digits, it really only makes sense to keep around 2 in the end. Okay. So scientists aren't going to include 9 significant digits thinking they're doing a better job. They actually know that that's worse. You're quoting numbers that don't make sense, that aren't trustable. So here we're going to see more specifically how to round numbers and so on. But I think it's pretty clear that 7.5 would probably be a good number to record for this. Okay. If you put a bunch of decimals, it'd be like, no, you can't trust those ones, right? So the rounding significant digits we'll do in class more. So I would just say, or not in class, but in the lesson in a second. So basically, like where those decimals coming from is probably pretty obvious. But if you're measuring on this one, best you're going to be able to do is say like approximately a certain number of centimeters, right? You can't really, maybe you could approximate the 1 decimal, but like I would argue that you could probably measure like 5 point something, but the point something is definitely error, has error in it. So I would argue that they should have had this be 6.5 or something, in which case I would put it here. The other one, I guess because they have the full length, that makes sense. But and then one more level of precision possible here, of course, and then all the way down to fractions of a millimeter, really, I would want to have, right? But the main idea is that the more divisions you have, the more you can pay attention to those fine details. You can't pay attention to the fine details with this one, right? You just can't. You don't have that available. So like scales, measuring down to like the 10th of a gram or 100th of a gram or 1,000th of a gram or so on, right? You think of some scales in the science class. Some scales have all the way down to the 3rd decimal place. Some only have to the 2nd decimal place, and so on. All right. So these questions here, we don't have to do these ones, but I'll whip through them. Person measured 5.4719 seconds. What level? The way to answer this question, you kind of have to have information about what kind of human reaction time you'd have. And it was misleading because the human reaction one here led me to click this one. But they're 5.47 seconds. I think you can approximate a fraction of a second, right? So in order to, if reasonably, I'd say you can approximate that. I would like this answer to say 5 minutes 5 minutes 47 seconds, 0.2 second or whatever, because humans' reaction time can measure down to a 1/10 of a second or so. That would make more sense, right? If they had it written that way. This one here is like a hit and miss for this one. They basically say that like this older technology of a stopwatch, why isn't it used anymore, and so on. So it's less precise, inaccurate. The older technology made less precise and less accuracy. Not really. You can still see where the needle ends up, right? No one can read the sweeping dial. We only understand digital. Like, I hope that's not the case. Sometimes it's the case for time these days for people, but analog clocks are a challenge for some people these days. It's worrying to me. The cost of traditional handmade timepieces is a lot more than mass-produced electronic stopwatches, and that's the one that makes sense. Okay, obviously they're not recording metric time and so on. Question: we have person says they measure the needles between 52 and 53, picks up dumbbells and they mark 10. So measurements all in kilograms. Yeah, sounds about right. Person reports the numbers, the scale is 52.5. That sounds reasonable. Ideally, these are accurate, but they don't need to be extremely precise. Makes sense, right? You pick up a 10 kilogram weight, it doesn't have to be exactly down to the 5th decimal place or anything. There'd be little benefit at all if it included decimal places. I kind of agree with all of those, right? kind of weird to have the masses labeled down to the 5th decimal place or something. Car speedometer, 90 kilometers per hour. Is it inaccurate? Very precise. In doubt, since there's not a decimal place. This one's a little bit unfair. Like, you haven't really done this one yet, but this is the correct answer that they're saying here. I would like this one to be more like, would it be better if it had 7 decimal places? And the answer would be no. Okay, but if you converted to meters per second, it would be that value. We'll see that later on more specifically. This one goes along with the idea of the speedometer, though, not having all those decimal places, right? So it doesn't have all the way down to the decimals to make the speed and altitude easy to read for pilots, right? It's not about saving money. It's not avoiding confusing pilots who, of course, don't understand decimals, whatever, and so on. So basically, easy to read. And then what's our last one here? Oh, tire manufacturer, 30 psi. The gauge reads between 25 and 26. Estimates the measurement to be 25.5. What would our conclusion be here? So, since there's only one significant digit, does that mean it would round to 30, so the pressure is perfect? I'd want my tire pressure to be maybe a little more accurate than that. Driver does not remember taking account, does not remember taking out any air pressure, so that must be fine. Pressure gauge is not digital, so it can't be trusted. The pressure gauge might be misreading the tire. He decides to reset it and records another reading and so on to confirm. That would be like the best plan, right? So that's the little activity pages. And I like going through that because the idea of like where you're getting these decimals from becomes a lot more obvious, right? So significant digits. What do we do? What do we keep? And so on, right? Significant digits. The definition you want to know is it's the total number of digits in a measurement. So if you take a measurement, you're going to include all the ones that are for sure, plus you're also going to include that smallest, tiniest one that's an estimate. That's why I'm saying from a meter stick with millimeter scale, I would hope that someone would take the care to measure down to a fraction of a millimeter maybe even. Okay. That being said, if you gave two people the same meter stick and asked them to measure something, they might not correctly identify all down to the smallest millimeter. And so maybe that millimeter is well justified being thought of as the estimate. But personally, if I was measuring and trying to be really accurate, I know I could try to estimate a fraction of a millimeter. So it's debatable on the number you would keep. But once you've recorded them, the number of significant digits is all of those numbers, essentially, right? So any measured value has some errors, the idea, right? Where you keep one estimated number. Versus if you're counting something, counting numbers are considered exact. So if you had like 6 chairs in a room, you don't limit your other measurements and calculations and so on only to one significant digit because you just had a 6, right? 6 is just one number, but it's considered, it doesn't count really for number of significant digits, okay? But if you're measuring something at 5.3 centimeters, the 3 must have been like an estimate in that case. So you might have been using a meter stick that has just the centimeter divisions. You're approximating to be about 5.3. And that's the idea. So there's decisions that have been made based on the measurement situation, and that's why there are a certain number of decimals kept in the first place in the numbers you're using. Okay, so it's important the results of the calculations are rounded so that only one estimated value is kept. You can't have more precision in your answer than what you started with as well, right? So when you look at your calculations and your results, you can't include more precision in a result than something you started with. That just doesn't make sense. Okay, so for example here, if you have an area of 5.2 and a length of a rectangle or something and a length of 3 meters, and you calculate the width. If I calculate the width, I would just put the numbers in, divide out, solve for the width, and I get a width of 1.733333333 forever. Obviously, we don't have an infinite amount of precision somehow magically. And so we would say, okay, well, look at here, there's 2 significant digits in each of these things. And so obviously we would scratch out a whole bunch of those 3s and keep a reasonable amount of decimals, right? So what we're going to be doing very specifically leads to us saying, well, we would actually quote it as 1.7 because 2 significant digits in both the ones to start. And so 2 significant digits in the end is what you're supposed to keep, which makes sense, right? Before we go on, I'll just make sure you're aware of there's a rule about rounding for decimal 5s or any 5s really. If you're rounding up all the way for 5s, you would round up 5 times. You'd only round down 4 times. So you'd be rounding up more often than you round down. So there's an extra rule for rounding. If it's a 5, you're rounding out, and it's the digit to the left. You round down if it's even. In other words, you leave it as even, or you round up if it's odd. Okay, so 7.75, I would round up to 7.8, or 7.45, I'd leave it 7.4. An easier way to think of that is you're always just going to round so that the number is even. And that basically makes it so that half the time you're rounding up, half the time you're rounding down for this middle number, which makes it 4.5 round ups and round downs. Okay, so that's a little extra rule. The original version of the online course, when I used the actual D2L material, had a ton of questions in the homework where the answer that you put in digitally would be counted as wrong if you rounded wrong based on the 5-digit rule. And it drove my students and me crazy. So one of the benefits of doing my own thing here and showing you things, hopefully it's helpful for you to have a teacher really explaining things to you, and you're not suffering from a computer program that's programmed maybe not ideally. So how many numbers to keep, right? The really specific nitty-gritty details. For adding and subtracting numbers, you look at the number of decimal places, and that's been obvious in what we've done. So these two numbers here, you only have 2 significant digits in the 3.1, and there are, not significant digits, 1 decimal place, right? 1 decimal place in that, and then there's 4 decimal places in this. We're not talking about significant digits actually yet, okay? So basically the idea that's pretty logical, because if you look at this, you have 3.1, and then you don't know. You didn't measure carefully enough to have any idea what these numbers are. And so if you're adding them to a 3 and a 9 and a 7 that were very, very carefully measured with a high level of precision, right? You're adding a 3 to a no clue, and a 9 to a no clue, and a 7 to a no clue. So clearly these do not mean anything. Okay, so we would scratch those out and, round this to an 8, right? Because that's maybe, around that 7 that's there up to be at 8, of course. Let me make it so you can see the 7 a little bit better. Okay, but the idea is hopefully clear to you. Okay, so you'd round that as quoted as a 7.8. Okay, note that if it was 7.75, it would round to 7.8. If it was 7.65, it would stay at 7.6. Okay, again, not going to hammer you on those and take away a bunch of marks or anything, but it'd be awesome to see proper rounding to that level from students. So the add subtract rule is about decimal places. The multiply and divide rule, so getting the 4 versions of 4 operations in arithmetic out of the way here, right? Add, subtract, group together. You're concerned about decimals. With multiply and divide, we're worried about the number of significant digits. Okay, and so first we have to establish how many significant digits there are. So the rule for this, there's different sort of scenarios to cover. It's not really rules, but if you have all non-zeros, right, those clearly must all be significant. They're all just numbers. And what you have there is you have a measurement all the way down to the 1,000th. You approximated a 9. So that's an estimated number, the 9, and then the rest are locked in, really. Okay, so you've kept 3 exact and 1 estimated number. And so that's 4 significant digits. All non-zeros are significant. If you're looking at measuring something and it was 45.300, the only reason for putting those zeros in would be to specify how careful you were, right? How precise you measured things. So those zeros are significant. So the rule generically would be zeros to the right of the decimal indicate precision, so they're significant. Or sometimes people just say zeros to the right are significant digits with no justification, which is not a great way to try and learn things and understand things. So I'm hoping me explaining why they would be there is helping you. Okay. Another rule here is that it says zeros between non-zeros are significant. So obviously you have 4,003, the 3 being an estimated number. The zeros are locked in; they can't change, right? So those zeros are fine; they're significant digits. So they're trapped between numbers; they're significant. And the weird situation is when you have placeholder zeros. So 0.0000013. Those zeros are just holding place. We really only have 2 real numbers there, right? Not that zeros aren't real numbers, but actually there's some weird stuff about that in math, but we're not worried about that. So there's an episode of Young Sheldon actually where Sheldon starts to be worried by the idea that the zero isn't a real number. You might have seen it. The 1 and the 3 are numbers bigger than 0, or concrete numbers, if you will, and so there's two significant digits there. Those are just holding in place. With a number like 21,000, we're not sure, right? So it's like we're not sure whether it was approximately 21,000. Like if you're trying to approximate the number of blades of grass in a square meter, and you do some kind of like estimation, or maybe it was more precise. Maybe it's like exactly 210 for or 20. What do you say? 21,000 and not another 100 or whatever. I don't know how to word that right now, but basically, any number of those could be indicating precision, right? All the way down to even like if it was $21,000 and not a penny more. A little easier to explain in that scenario, right? Each of these could represent each of those results, right? So if it's literally just approximately 21,000, then it would be this one, right? So if it was approximately 21,000, I'll put a green arrow to this one here, right? If it was 3 significant digits, then that would be this one, right? That would be 3 significant digits. And then this one would be 4 significant digits, and so on all the way up, right? So finally, cutting to the chase here, the 7 significant digits would be this one. Okay, so if you wanted to specify $21,000, my numbers here times 10 to the 3, yeah, it's not great the way this is written, but it's just the example I'd used. It should be like 2.1 times 10 to the 4. Okay, just for proper scientific notation. But I was focusing on those 3 zeros. That's why I did it that way. So I was just second guessing myself here for a bit, realizing like it's not ideal. But anyways, so we have the 21, and then 0.000 times 10 to the 3. If you notice that decimal place would move 1, 2, 3 spots and be there, representing that $21,000 down to the nearest cent. Okay. So scientific notation is pretty awesome for helping communicate level of precision. So it's a new benefit that you might not have thought of. You've probably heard of scientific notation, where scientific notation is great for representing really big and really small numbers, but it's also really good for making the number of significant digits obvious. Okay, so yeah, that's the big small number stuff, but yeah. On your calculator, if you need to get some help with that, look up YouTube videos about this, I'm sure, but you can do 10 to the power of, literally, so 10 to the power of 3 and so on. Or you can use your EE button. So iPhones and TI-83s and so on have a special EE button that does a 10 to the for you. It's a little bit nicer. It's a little more reliable. Sometimes calculators would get confused if you typed this all in with the 10 to the power, and it might think you meant 10 to the power of 3 times, and so on. Whereas if you use your EE button, it tends to be a little more reliable. But a nice way to do this as well is just to multiply the numbers and work with the 10 to the power exponent stuff. You can even use your power rule stuff from math class. Okay, so this example shows how you could operate or do the operations here. Okay, yeah. So I'll just leave that. If you need help with that, I can do an extra tutorial video about using the calculator for these things. So I'm not really thinking I want to extend this lesson video that long. So I need to get back to this add, multiply, divide rule, right? We're keeping the same number of significant digits in the result as the least there were in the measurements. So it's a heck of a lot like the add subtract one, where we're keeping the least number of decimals that there were in the ones you started with, but instead we're keeping the least number of significant digits. So if we're multiplying, the classic rounded version of pi, that's 3 significant digits. The other number has 5, and so we would keep 3. Round the 7, leave it as a 7, right? Round it down to a 7. Here, 4 significant digits, and this one is clear that there's 7 because the zeros are there to indicate precision. Dividing led to this. We'd round to 4 significant digits, right? The least number there were in what you started with. If this is a measured number, you round to just 1 significant digit. So in other words, if this is literally approximately 6, then the answer would be around 2. Just that's the level of information you can trust. If this is a counted number, then you would keep 3, and so it would be 1.54. Okay, because you don't limit precision based on a counted number. So hopefully that makes sense to you. I don't want you to be super stressed about all of it. And so the good news is, in this class, generally, I want you to round reasonably. Overall, if I see you keeping 17 decimal places, I'm obviously going to maybe comment and take a mark off if necessary in the question, and depending on the context, right? So generically, just round reasonably. Use the ideas we've done as a guide, at least roughly. In some questions, I'm going to have an additional part of the question, so part C kind of thing or whatever, where you'll be graded specifically on the precise, exact rules of rounding and significant digit keeping. Okay, so that'll be like an extra mark in some questions now and then to basically assess your ability and your knowledge of this stuff. Okay. And the other note is textbook numbers always are assumed to be three significant digits. So if they just said 20 centimeters, what they're meaning is 20.0. So there's a bit of a possible seeming inconsistency seeming to be happening maybe in some areas of the textbook, and that's why. All right. So these are your questions to do. There's even answers there to help you along the way. If you want more practice, there's one down the bottom as well. Hopefully that works for you. And yeah, that's it for now. Thanks for watching.